Subscribe to Boring Science for sleep for new videos every day. Now, let us begin. Deep beneath the surface of the Earth, in places where sunlight has never reached and where the air remains still and undisturbed for centuries at a time, there exist formations of mineral deposits that have been slowly accumulating since long before the earliest recorded histories of human civilization. These formations, collectively referred to by geologists and speleologists as speleothems, are the product of an extraordinarily gradual chemical process that unfolds over timescales so vast that they are, for all practical purposes, nearly incomprehensible to the human mind. The word speleothem itself is derived from the Greek word speleon, meaning cave, and thema, meaning deposit, and it was first introduced into the scientific literature in the year 1952 by the geologist G. W. Moore, who recognized the need for a single unifying term to describe the many varieties of mineral formations found within the interiors of caves throughout the world. The most widely recognized and commonly encountered speleothems are, of course, stalactites and stalagmites, those familiar icicle-shaped and mound-shaped formations that hang from the ceilings and rise from the floors of limestone caves, respectively. However, the full catalog of speleothem types is considerably more extensive than these two well-known examples might suggest, encompassing such formations as flowstone, draperies, columns, rimstone dams, cave pearls, helictites, and numerous other varieties, each of which is formed through slightly different mechanisms and under slightly different environmental conditions. All of these formations, however, share a common fundamental origin in the chemistry of calcium carbonate, the mineral compound that constitutes the primary building material of limestone rock, and that serves as the basis for nearly all cave decoration found in karst landscapes around the globe. To understand how stalactites and stalagmites come into being, it is first necessary to understand the chemistry of calcium carbonate, a compound with the chemical formula CaCO3, which is one of the most abundant minerals found on the surface of the Earth. Calcium carbonate occurs naturally in several crystalline forms, the most common of which are calcite and aragonite. Calcite, which belongs to the trigonal crystal system and has a Mohs hardness of approximately 3, is by far the more prevalent of the two in cave environments, and it is the mineral from which the vast majority of stalactites and stalagmites are composed. Aragonite, which shares the same chemical formula but crystallizes in the orthorhombic system, is less commonly encountered in caves, but does occur under certain specific conditions of temperature, pressure, and chemical composition that will be discussed at a later point in this narration. The story of stalactite and stalagmite formation begins not inside the cave itself, but rather on the surface of the Earth, high above the cave, where rainwater falls from the sky and begins its slow journey downward through the soil and rock. Rainwater, as it descends through the atmosphere, absorbs small quantities of carbon dioxide gas from the air. The concentration of carbon dioxide in the Earth's atmosphere is currently approximately 420 parts per million, although this value has fluctuated considerably over geological time, and the amount of carbon dioxide dissolved by any given raindrop is influenced by factors such as atmospheric pressure, temperature, and the partial pressure of carbon dioxide in the surrounding air. When carbon dioxide dissolves in water, it undergoes a chemical reaction that produces carbonic acid, a weak acid with the chemical formula H2CO3. This reaction can be expressed as CO2 plus H2O yielding H2CO3, and it proceeds readily under the conditions that prevail at the Earth's surface. However, the concentration of carbon dioxide in the open atmosphere is relatively modest, and the amount of carbonic acid formed by rainwater falling through the air alone would be insufficient to dissolve limestone at any appreciable rate. The critical step in the process occurs after the rainwater has reached the ground and has begun to percolate downward through the soil. The soil layer, particularly in temperate and tropical regions where vegetation is abundant, contains concentrations of carbon dioxide that are dramatically higher than those found in the open atmosphere. This elevated concentration is the result of biological activity within the soil, including the respiration of plant roots, the metabolic activity of soil microorganisms, and the decomposition of organic matter. In a typical temperate forest soil, the concentration of carbon dioxide may reach levels of 10,000 to 100,000 parts per million, which is roughly 25 to 250 times greater than the concentration in the atmosphere above. As the percolating rainwater passes through this carbon dioxide-rich soil layer, it absorbs substantially more carbon dioxide, and the concentration of carbonic acid in the water increases correspondingly. This carbonic acid-enriched water, sometimes referred to by geologists as aggressive water because of its enhanced capacity to dissolve calcium carbonate, continues its downward journey through cracks, fissures, and pore spaces in the rock. When this mildly acidic water encounters limestone, a chemical reaction takes place in which the carbonic acid reacts with the calcium carbonate of the limestone to produce calcium bicarbonate, a compound with the chemical formula Ca, HCO3, 2, which is soluble in water. The reaction can be written as CaCO3 plus H2CO3 yielding Ca2 plus 2HCO3-, and it is this reaction that is fundamentally responsible for the dissolution of limestone and, ultimately, for the creation of the caves themselves. The calcium and bicarbonate ions produced by this reaction are carried along in solution by the moving water, and the limestone is gradually eaten away, molecule by molecule, over periods of time that span hundreds of thousands or even millions of years. The rate at which limestone dissolves is influenced by a number of factors, including the concentration of carbon dioxide in the water, the temperature of the water, the flow rate of the water, the surface area of limestone exposed to the water, and the initial purity and crystalline structure of the limestone itself. Pure limestone, composed almost entirely of calcium carbonate, dissolves more readily than impure varieties that contain significant admixtures of clay, silica, or other insoluble minerals. The temperature of the water also plays a role, as the solubility of carbon dioxide in water increases at lower temperatures, meaning that cooler water can dissolve more carbon dioxide and therefore more limestone than warmer water, all other factors being equal. This somewhat counterintuitive relationship has important implications for cave formation in different climatic zones. Although the higher biological activity in tropical soils often compensates for this effect by producing substantially higher soil carbon dioxide concentrations. Over geological timescales, this process of slow, persistent dissolution creates an increasingly complex network of underground passages, chambers, and voids within the limestone rock. The formation of a cave of significant size is an undertaking that requires an almost inconceivable amount of time. A typical limestone cave passage may take anywhere from 100,000 to several million years to develop to a size large enough for a human being to enter, depending on the local conditions of hydrology, geology, and climate. The Mammoth Cave System in Kentucky, which is the longest known cave system in the world with more than 680 kilometers of surveyed passages as of 2024, has been forming for approximately 10 million years. While the Carlsbad Caverns in New Mexico are estimated to have begun forming roughly 4 to 6 million years ago during the late Miocene and Pliocene epochs. These timescales are so enormous that they dwarf the entire span of recorded human history, which extends back only approximately 5,000 years, by a factor of roughly 1,000 or more. Once a cave has been formed and the water table has dropped sufficiently to leave air-filled passages above the standing water level, the conditions become favorable for the reverse of the dissolution process to begin. This reverse process, the precipitation of calcium carbonate from solution, is what gives rise to stalactites, stalagmites, and all the other varieties of speleothems that decorate the interiors of limestone caves. The mechanism is, in essence, the exact opposite of the dissolution reaction described previously. When water that is saturated or supersaturated with dissolved calcium bicarbonate seeps into the cave through cracks and pores in the ceiling, it encounters an environment in which the concentration of carbon dioxide in the air is lower than the concentration of carbon dioxide that was dissolved in the water while it was passing through the soil and rock above. This difference in carbon dioxide concentration drives the outgassing, or release, of carbon dioxide from the water into the cave atmosphere, and as the water loses carbon dioxide, the chemical equilibrium of the dissolution reaction shifts in the reverse direction, causing calcium carbonate to precipitate out of solution as a solid mineral deposit. The formation of a stalactite begins with a single drop of water that emerges from a crack or pore in the ceiling of the cave. As this drop of water hangs from the ceiling, a thin film of water is exposed to the cave air, and carbon dioxide begins to diffuse out of the water and into the surrounding atmosphere. The loss of carbon dioxide shifts the chemical equilibrium, and a microscopically thin ring of calcium carbonate is deposited around the point where the water drop is attached to the ceiling. When the drop eventually falls away, it leaves behind this tiny ring of mineral deposit, which is typically no more than a few micrometers in thickness. The next drop of water that forms at the same point adds another microscopically thin layer of calcium carbonate to the ring, and then the next drop adds yet another layer. And so the process continues, drop by drop, layer by layer. Over periods of time that are measured not in days or weeks or months, but in years and decades and centuries and millennia. In the earliest stages of its development, a stalactite takes the form of a thin, hollow tube known as a soda straw stalactite, so called because of its resemblance to a drinking straw. The soda straw form arises because the calcium carbonate is deposited primarily around the outer rim of the water drop, creating a hollow cylindrical structure through which subsequent drops of water can flow. A typical soda straw stalactite has an external diameter of approximately 5 to 9 millimeters, which corresponds closely to the diameter of a water drop hanging from a ceiling under the influence of surface tension and gravity. The internal diameter of the hollow tube is somewhat smaller, typically around 1 to 3 millimeters, and the walls of the tube are composed of crystalline calcite that has been deposited in concentric layers over time. Soda straw stalactites can grow to remarkable lengths if conditions remain stable. The longest known soda straw stalactite, found in a cave in Western Australia, measures approximately 6 meters in length, although most soda straw stalactites are considerably shorter, typically ranging from a few centimeters to perhaps a meter or so in length. As a soda straw stalactite grows longer, it becomes increasingly likely that the central tube will become blocked by mineral deposits or by impurities in the water, such as tiny particles of clay or organic matter. When the central tube becomes blocked, water can no longer flow through the interior of the stalactite and instead begins to flow down the outside surface. As this water flows over the exterior of the stalactite, it deposits calcium carbonate along the entire outer surface, and the stalactite begins to thicken and take on the more familiar conical or carrot-shaped form that most people associate with the word stalactite. The rate at which this thickening occurs is, like every other aspect of stalactite growth, extraordinarily slow. A typical stalactite may grow in length at a rate of approximately 0.1 to 0.3 millimeters per year, although rates as low as 0.01 millimeters per year and as high as 3 millimeters per year have been documented under different conditions. At a growth rate of 0.1 millimeters per year, a stalactite would require 10,000 years to grow a single meter in length, and some of the largest stalactites found in caves around the world, which may reach lengths of 10 meters or more, have been growing continuously for hundreds of thousands of years. The shape of a stalactite is determined by the pattern of water flow over its surface. If water flows relatively evenly over the entire surface, the stalactite will tend to develop a smooth, symmetrical, conical shape. If the flow is uneven, with more water flowing down one side than the other, the stalactite may develop an asymmetrical or irregular shape, with bulges, ridges, or protrusions on the side where the water flow is greatest. The cross-section of a stalactite, when cut perpendicular to its long axis, typically reveals a pattern of concentric growth rings, somewhat similar to the growth rings of a tree, with each ring representing a period of mineral deposition. These growth rings can vary in thickness, color, and mineral composition, and they provide a valuable record of the environmental conditions that prevailed at the time each ring was deposited. Thicker rings may indicate periods of greater water flow or higher calcium carbonate concentrations, while thinner rings may indicate drier periods or periods of reduced biological activity in the soil above the cave. The temperature inside a cave remains remarkably constant throughout the year, typically hovering within a degree or two of the average annual surface temperature above the cave. In temperate regions, this means that cave temperatures generally fall in the range of approximately 10 to 15 degrees Celsius, while in tropical regions, cave temperatures may be somewhat higher, in the range of 20 to 25 degrees Celsius. This thermal stability is one of the factors that contributes to the steady, uninterrupted growth of speleothems over geological timescales, as the chemical reactions involved in calcium carbonate precipitation are sensitive to temperature changes, and the constant temperature environment of a cave ensures that these reactions proceed at a consistent rate year after year, century after century. The humidity inside a cave is also typically very high, often approaching 100% relative humidity, which means that the rate of evaporation of water from the surfaces of speleothems is very low. This is an important consideration because, while evaporation can contribute to the precipitation of calcium carbonate from solution, the primary driving force for speleothem growth in most caves is the outgassing of carbon dioxide rather than evaporation. In caves where air circulation is minimal and the humidity remains close to saturation, the rate of evaporation is negligible, and virtually all of the calcium carbonate deposition is driven by the loss of carbon dioxide from the drip water. In caves that are more open to the outside atmosphere, where air currents may reduce the humidity somewhat, evaporation may play a more significant role in driving mineral precipitation, but even in such cases, carbon dioxide outgassing typically remains the dominant mechanism. The concentration of carbon dioxide in cave air is another factor that influences the rate of speleothem growth. In a sealed or poorly ventilated cave, the concentration of carbon dioxide may build up to levels significantly higher than the atmospheric concentration, as carbon dioxide is continuously being released from the drip water. In some caves, carbon dioxide concentrations of 1,000 to 10,000 parts per million or even higher have been measured, which is several times to several tens of times greater than the atmospheric concentration of approximately 420 parts per million. When the cave air already contains a high concentration of carbon dioxide, the rate of outgassing from the drip water is reduced, because the driving force for outgassing is the difference in carbon dioxide concentration between the water and the surrounding air. As a result, speleothem growth rates tend to be lower in poorly ventilated caves with high atmospheric carbon dioxide concentrations than in well-ventilated caves where the carbon dioxide is continuously swept away by air currents. Each individual drop of water that falls from a stalactite carries with it a tiny amount of dissolved calcium bicarbonate that was not precipitated during the brief time the drop was in contact with the cave ceiling. The exact amount of calcium carbonate that is deposited by each drop depends on the degree of supersaturation of the water, the time the drop spends in contact with the stalactite, the temperature, the humidity, and the carbon dioxide concentration in the cave air. A single drop of cave drip water typically contains between 100 and 400 milligrams per liter of dissolved calcium carbonate, and each drop deposits only a fraction of this total, perhaps 10 to 30%, as it forms and falls from the stalactite. The remainder of the dissolved calcium carbonate is carried away in the drop as it falls to the cave floor, where it becomes available for the formation of a stalagmite or other floor deposit. The interval between successive drops varies enormously from one drip site to another, and can also vary at the same drip site over the course of a year, depending on seasonal variations in rainfall and groundwater levels. At some drip sites, water may fall at a rate of several drops per minute, while at others, the interval between drops may be several minutes, hours, or even days. The drip rate has a complex relationship with the rate of speleothem growth, as higher drip rates provide more water and therefore more dissolved calcium carbonate. But the shorter contact time between each drop and the stalactite may reduce the percentage of calcium carbonate that is deposited per drop. Conversely, slower drip rates provide less water overall, but allow each drop more time to degas carbon dioxide and deposit calcium carbonate before falling. The interplay between these competing factors means that the relationship between drip rate and growth rate is not a simple linear one, and the optimal drip rate for maximum growth depends on the specific conditions at each drip site. It is worth pausing to consider just how slow and gradual this entire process truly is. If one were to stand in a cave and watch a stalactite for an entire day, one would observe nothing whatsoever happening to it, apart from the occasional drip of water falling from its tip. If one were to return a year later, the stalactite would appear entirely unchanged, because the amount of growth that occurs in a single year is far too small to be detected by the unaided human eye. Even if one were to visit the same stalactite once a decade for an entire human lifetime, the cumulative growth over that period would amount to no more than a millimeter or two at most, which would still be barely perceptible without the aid of precise measuring instruments. It is only over the span of centuries and millennia that the slow accumulation of mineral deposit becomes visible as a noticeable change in the size and shape of the formation. And it is only over the span of tens of thousands or hundreds of thousands of years that stalactites grow to the impressive dimensions that are observed in the great show caves of the world. The geological record preserved within stalactites and other speleothems is, for this very reason, one of extraordinary detail and temporal resolution. Because each layer of calcium carbonate was deposited under a specific set of environmental conditions, and because the chemical and isotopic composition of each layer is influenced by factors such as temperature, rainfall, vegetation cover, and atmospheric carbon dioxide concentration, Speleothems serve as remarkably faithful archives of past climate conditions. This application of speleothem science, known as paleoclimatology, has become one of the most important and active areas of speleological research in recent decades, and it will be discussed in greater detail at a later point in this narration. For now, it is sufficient to note that the same properties that make stalactite growth so agonizingly slow, namely the sensitivity of the deposition process to environmental conditions and the remarkable stability of the cave environment, also make stalactites and other speleothems among the most valuable natural records of past climate that are available to scientists. The chemistry of the precipitation process itself involves several intermediate steps that are worth describing in some additional detail, if only because the sheer number of individual chemical reactions taking place at the surface of a growing stalactite is itself a subject of some quiet fascination. When a drop of water saturated with calcium bicarbonate emerges from the ceiling of a cave, the first reaction that occurs is the loss of dissolved carbon dioxide from the water to the cave atmosphere. This outgassing reaction can be written as H2CO3 yielding H2O plus CO2, and it proceeds because the partial pressure of carbon dioxide in the cave air is lower than the partial pressure of carbon dioxide in the drip water. As carbon dioxide is lost from the water, the pH of the water increases, becoming less acidic, and the water becomes supersaturated with respect to calcium carbonate. At this point, the precipitation reaction occurs, in which calcium ions and carbonate ions in solution combine to form solid calcium carbonate crystals on the surface of the stalactite. The overall reaction can be summarized as Ca2++ 2HCO3, yielding CaCO3 plus H2O plus CO2, which is simply the reverse of the dissolution reaction that took place when the water was passing through the limestone above the cave. The crystals of calcium carbonate that are deposited on the surface of a growing stalactite are typically very small, on the order of a few micrometers in size, and they're arranged in a variety of crystallographic orientations depending on the conditions of precipitation. In many stalactites, the calcite crystals are arranged with their c-axis oriented parallel to the long axis of the stalactite, creating a fibrous or columnar texture that can be observed in thin sections under a polarizing microscope. This preferential orientation of the crystals is thought to result from competitive growth, in which crystals that happen to be oriented with their fastest growing direction pointing outward from the surface of the stalactite gradually outcompete and overgrow crystals in other orientations, producing a texture in which all of the surviving crystals share a similar orientation. The color of a stalactite is determined primarily by the presence of trace impurities in the calcium carbonate. Pure calcium carbonate is white or colorless, and stalactites composed of very pure calcite tend to be white or translucent. However, most stalactites contain small amounts of impurities that impart various colors to the formation. Iron oxides and hydroxides are among the most common coloring agents, producing shades of yellow, orange, brown, and red, depending on the oxidation state and concentration of the iron. Manganese oxides can produce dark brown or black coloration, while organic matter derived from the soil above the cave can impart yellow or brown tones. In some caves, stalactites may display banding of different colors, reflecting changes in the concentration of impurities in the drip water over time. And these color bands can sometimes be correlated with seasonal or longer-term environmental cycles. The process of stalactite formation, as has been described in the preceding paragraphs, is one of almost incomprehensible patience. A process in which the earth itself seems to be engaged in a project of construction so vast and so slow that it makes the building of the Great Pyramids of Egypt seem like a hasty weekend undertaking by comparison. Each drop of water that forms on the ceiling of a cave hangs for a moment, and then falls to the floor below is a tiny participant in a geological drama that has been unfolding for millions of years, and that will continue to unfold for millions of years into the future, long after the last human being has departed from the surface of the earth. There is, perhaps, something oddly comforting in the contemplation of processes that operate on such timescales, processes that are utterly indifferent to the concerns and anxieties of daily human life, processes that proceed with the same unhurried steadiness whether anyone is watching them or not, whether anyone cares about them or not, whether anyone even knows they are happening or not. When a drop of water that has been hanging from the tip of a stalactite finally succumbs to the force of gravity and detaches itself from the formation above, it begins a brief descent through the still air of the cave, falling at a gradually increasing velocity until it strikes the floor of the cave below. The height of this fall varies considerably from one cave to another, and even from one location to another within the same cave, ranging from as little as a few centimeters in low-ceilinged passages to as much as 50 meters or more in the great vertical shafts and domed chambers that are found in some of the world's more spectacular cave systems. The typical height of fall in most cave passages, however, is on the order of 2 to 10 meters, and the drop of water arrives at the floor with a small but measurable impact that causes it to splash and spread outward in a thin film across the rock surface. This drop of water, as has been previously noted, still contains a substantial fraction of the dissolved calcium bicarbonate that it was carrying when it first emerged from the ceiling of the cave. The process of carbon dioxide outgassing, which drove the precipitation of calcium carbonate on the stalactite above, continues as the drop falls through the cave air and after it lands on the floor. Upon impact with the cave floor, the drop is deformed and spread into a thin film, which greatly increases the surface area of the water that is exposed to the cave atmosphere, thereby accelerating the rate of carbon dioxide loss. As additional carbon dioxide diffuses out of the water and into the cave air, the water becomes further supersaturated with respect to calcium carbonate, and mineral precipitation occurs on the floor of the cave at the point where the drop landed. This is the fundamental mechanism by which stalagmites are formed. Just as a stalactite grows downward from the ceiling of a cave by the accumulation of calcium carbonate from dripping water, A stalagmite grows upward from the floor of the cave by the accumulation of calcium carbonate from the same dripping water after it has completed its descent from the stalactite above. The two formations are, in a very real sense, partners in the same geological process, fed by the same source of water and growing simultaneously, one reaching downward and the other reaching upward, like two halves of a handshake that will not be completed for another 100,000 years. The shape of a stalagmite differs characteristically from the shape of a stalactite, and this difference arises from the different geometry of water flow on the two types of formation. On a stalactite, water flows downward along the outer surface under the influence of gravity, producing the familiar elongated, tapering, conical shape. On a stalagmite, however, the water arrives from above as discrete drops that splash and spread outward upon impact, and the resulting flow pattern produces a formation that is generally broader and more rounded than a stalactite. A typical stalagmite has a roughly cylindrical or slightly tapered shape, with a rounded or domed top and a broader base, and its width is generally a larger fraction of its height than is the case for stalactites. The exact shape of any individual stalagmite depends on the drip rate, the height of fall, and the local conditions of airflow and humidity, and stalagmites can range in form from tall, narrow pillars to broad, squat mounds. The growth rate of a stalagmite is comparable to that of the stalactite from which it receives its water supply, typically falling in the range of 0.1 to 0.3 millimeters per year under average conditions. However, the growth rate of a stalagmite is not necessarily identical to that of its corresponding stalactite, because the amount of calcium carbonate deposited at each location depends on the local conditions of carbon dioxide outgassing. A significant fraction of the total carbon dioxide lost from the water may occur while the drop is hanging from the stalactite, and a further fraction is lost during the fall and upon impact with the stalagmite. The partitioning of calcium carbonate deposition between the stalactite and the stalagmite depends on the relative rates of carbon dioxide outgassing at each location, which in turn depend on factors such as the ventilation of the cave, the height of the ceiling, and the drip rate. Some of the largest stalagmites in the world are truly impressive in their dimensions, having been growing steadily for hundreds of thousands of years. The tallest known stalagmite is located in the Zhejiang Cave in Guizhou Province, China, and it measures approximately 70 meters in height, which is roughly the height of a 20-story building. Other notably large stalagmites include a formation in the Krobra Cave in Georgia that stands approximately 28 meters tall, and several stalagmites in the caves of Borneo that exceed 20 meters in height. The formation of such massive structures requires an almost unimaginable duration of continuous growth, and stalagmites of this size have typically been growing for 500,000 years or more, with some estimates suggesting growth periods of several million years for the very largest examples. When a stalactite growing downward from the ceiling and a stalagmite growing upward from the floor directly below it eventually come into contact with each other and merge, the resulting formation is known as a column or sometimes as a pillar. The formation of a column represents the completion of a process that may have been underway for hundreds of thousands of years, and columns can be among the most massive and imposing speleothems found in caves. Once a column has formed, water continues to flow over its outer surface, depositing additional layers of calcium carbonate and gradually increasing its diameter over time. Some columns in large cave chambers have diameters of several meters and heights of 20 meters or more, representing the accumulation of billions of individual drops of water over spans of geological time. In addition to stalactites, stalagmites, and columns, caves contain a rich variety of other speleothem types, each formed by a slightly different variation of the same basic chemical process. Flowstone is a sheet-like deposit of calcium carbonate that forms where water flows in a thin film over the walls, floors, or other surfaces of a cave, rather than dripping from the ceiling as individual drops. Flowstone can cover large areas of a cave's interior surfaces and can build up to considerable thicknesses over time, sometimes reaching several meters in depth. The surface of flowstone is typically smooth and undulating, with a texture that has been compared to frozen waves or to the surface of a melted candle, and it may display the same color banding that is observed in stalactites, reflecting variations in water chemistry over time. Draperies, also known as cave curtains or cave bacon, are thin, translucent sheets of calcium carbonate that hang from the ceilings or walls of caves in graceful, undulating folds that resemble curtains or strips of fabric. Draperies form when water flows along the underside of an inclined ceiling, following a path that is determined by the slope of the rock surface and by slight irregularities in the ceiling texture. As the water flows along its path, it deposits a thin line of calcium carbonate, and over time, this line of deposit grows downward to form a thin, blade-like sheet that hangs vertically from the ceiling. The undulating or wavy form of draperies results from slight variations in the path of water flow over time, which cause the line of deposition to shift back and forth across the ceiling, producing a sheet that is not flat but instead has a corrugated or folded appearance. When illuminated from behind, draperies can be strikingly translucent, and the alternating bands of lighter and darker calcite that run along the length of the drapery give it an appearance that has led to the common name cave bacon, which, while perhaps somewhat whimsical for a geological formation, does provide a reasonably accurate visual description. Rimstone dams, also known as gores, are another common type of speleothem that forms on the floors of caves where thin films of water flow over gently sloping surfaces. Rimstone dams are curved or semicircular barriers of calcium carbonate that form at the edges of shallow pools of water, creating a series of terrace basins that resemble a staircase of miniature swimming pools. The formation of rimstone dams is driven by the same chemical process of carbon dioxide outgassing and calcium carbonate precipitation that drives the formation of stalactites and stalagmites, but the specific geometry of the formations is determined by the hydrodynamics of thin film flow over the cave floor. At the downstream edge of each pool, where the water flows over the rim and drops to the next lower pool, The turbulence of the flowing water enhances the rate of carbon dioxide outgassing, leading to preferential deposition of calcium carbonate at the rim, which causes the rim to grow higher over time and the pool behind it to grow deeper. Rimstone dams can range in size from tiny formations only a few millimeters in height to massive structures several meters tall that impound pools of water several meters deep. The factors that affect the growth rates of all these various types of speleothems are numerous and interrelated, and understanding these factors is essential for interpreting the geological and climatological information that speleothems contain. The concentration of carbon dioxide in the soil above the cave is perhaps the single most important factor, as it determines the amount of calcium carbonate that can be dissolved by the percolating water and therefore the amount of calcium carbonate that is available for deposition in the cave below. Soil carbon dioxide concentrations are strongly influenced by biological activity, which in turn is influenced by temperature, moisture, and vegetation type. In general, warmer and wetter climates support greater biological activity in the soil, leading to higher soil carbon dioxide concentrations, greater dissolution of limestone, and faster speleothem growth rates. During glacial periods, when temperatures were lower and vegetation was sparser in many regions, soil carbon dioxide concentrations would have been reduced, and speleothem growth rates would have correspondingly decreased. In some caves, speleothem growth ceased entirely during glacial periods, either because the reduced availability of water in arid glacial climates eliminated the supply of drip water, or because the cave was overridden by glacial ice. The flow rate of water through the cave system is another critical factor. Higher flow rates deliver more dissolved calcium carbonate to the cave per unit time, potentially increasing the rate of speleothem growth. However, as has already been noted, higher flow rates also reduce the contact time between each drop of water and the speleothem surface, which may reduce the fraction of dissolved calcium carbonate that is deposited per drop. Additionally, very high flow rates can lead to erosion rather than deposition, as the mechanical energy of the flowing water may be sufficient to dissolve or physically remove previously deposited calcium carbonate. The relationship between flow rate and growth rate is therefore nonlinear, and there exists an optimal flow rate at which the rate of calcium carbonate deposition is maximized for any given set of chemical and environmental conditions. Temperature affects speleothem growth through several mechanisms. As previously mentioned, the solubility of carbon dioxide in water decreases with increasing temperature, which means that warmer water can hold less dissolved carbon dioxide and will therefore tend to outgas carbon dioxide more readily when it enters the cave. This effect tends to increase the rate of calcium carbonate precipitation at higher temperatures. However, the overall amount of calcium carbonate available for deposition depends on the amount that was dissolved in the first place, which is greater at lower temperatures where carbon dioxide is more soluble. The net effect of temperature on speleothem growth rate is therefore the result of a balance between these opposing influences, and it varies depending on the specific conditions at each cave site. The ventilation of the cave, which refers to the exchange of air between the cave interior and the outside atmosphere, also plays an important role in controlling speleothem growth rates. In a well-ventilated cave, carbon dioxide that is released from the drip water into the cave atmosphere is continuously carried away by air currents and replaced with lower carbon dioxide outside air, maintaining a large difference in carbon dioxide concentration between the drip water and the cave air, and thereby promoting rapid outgassing and mineral deposition. In a poorly ventilated cave, carbon dioxide accumulates in the cave atmosphere, reducing the concentration gradient and slowing the rate of outgassing. Many caves exhibit seasonal variations in ventilation that are driven by differences in temperature between the cave interior and the outside air. During winter, when the outside air is colder and denser than the cave air, cold outside air sinks into the cave and displaces the warmer, less dense cave air, creating a chimney effect that enhances ventilation. During summer, when the outside air is warmer than the cave air, this driving force is reversed, and ventilation may be reduced or even eliminated, allowing carbon dioxide to build up in the cave atmosphere. These seasonal variations in ventilation can produce corresponding seasonal variations in speleothem growth rates, with faster growth during the well-ventilated winter months and slower growth during the poorly ventilated summer months. This seasonal cycling of growth rates can produce visible laminations in the structure of speleothems, with each pair of laminations, one representing a period of faster growth and one representing a period of slower growth, corresponding to a single year. These annual laminations are analogous to the annual growth rings of trees, and they can be counted to determine the age of a speleothem with a precision that is sometimes better than that achievable with radiometric dating methods. The stability of the cave environment is one of the most remarkable features of these underground spaces, and it is this stability that allows speleothems to grow continuously and without interruption for periods that may span hundreds of thousands of years. The temperature inside a deep cave varies by no more than a fraction of a degree over the course of an entire year, and the humidity remains at or near 100% at all times. There are no seasons inside a cave, no storms, no droughts, no floods, no forest fires, and no ice ages, at least not in the sense that these events are experienced on the surface. The only connection between the cave environment and the surface world above is the thin trickle of water that seeps through the rock, carrying its dissolved cargo of calcium and bicarbonate ions, and the slow exchange of air through cracks and passages that connects the cave atmosphere to the outside. This isolation from surface disturbances is what makes caves such exceptionally stable environments and what allows speleothems to accumulate as faithful, uninterrupted records of environmental conditions over immense spans of time. The cave environment also supports a surprising diversity of life, despite the perpetual darkness and the apparent scarcity of food resources. Cave-dwelling organisms have been the subject of scientific study for more than 2 centuries, and the ecological communities that inhabit caves are now recognized as being among the most specialized and unusual in the natural world. However, The biological aspects of caves will be discussed in greater detail in a subsequent portion of this narration, as the present discussion is concerned primarily with the physical and chemical processes of speleothem formation. It is perhaps appropriate at this point to note that the distinction between stalactites and stalagmites, while straightforward in principle, has been a source of mild confusion for generations of students, tourists, and members of the general public. A stalactite hangs from the ceiling, growing downward, while a stalagmite rises from the floor, growing upward. Various mnemonic devices have been proposed over the years to help people remember which is which, the most common of which relies on the observation that stalactite contains the letter C, which can stand for ceiling, while stalagmite contains the letter G, which can stand for ground. Another common mnemonic notes that stalactites hold tight to the ceiling, while stalagmites might grow up to meet them. These devices, while lacking in scientific rigor, have proven remarkably effective at their intended purpose. And it is likely that a substantial fraction of the world's population that knows the difference between these two types of formations learned it through one or another of these simple memory aids. The word stalactite is derived from the Greek word stalactos, meaning dripping or that which drips, while the word stalagmite is derived from the Greek word stalagma, meaning a drop or a dropping. Both words were introduced into English in the late 17th century, with stalactite first appearing in print in approximately 1677 and stalagmite following shortly thereafter. The study of caves and their formations, now known as speleology, has a much longer history, however, with references to caves and their mineral deposits appearing in the writings of ancient Greek and Roman scholars, including Pliny the Elder, who described cave formations in his encyclopedic work Naturalis Historia, published in approximately 77 AD. The cross-sectional structure of a stalagmite, when examined under a microscope or by cutting the formation in half along its vertical axis, reveals a pattern of layered deposition that provides important information about the history of the formation's growth. Unlike the concentric rings of a stalactite, which are arranged around a central hollow or solid core, the layers of a stalagmite are arranged as a series of roughly dome-shaped caps, one stacked on top of another, with the oldest layers at the bottom and the youngest layers at the top. This layered structure reflects the fact that each successive layer of calcium carbonate is deposited as a thin film that covers the top surface of the stalagmite and drapes down over its sides, like a series of tablecloths or blankets laid one on top of another. The thickness of each layer varies depending on the rate of mineral deposition at the time, and the composition and color of each layer reflect the chemistry of the drip water from which it was precipitated. When a stalagmite is cut in half vertically and polished, the exposed cross-section often displays a striking pattern of alternating light and dark bands, which represent variations in the composition or texture of the calcite from layer to layer. These bands may be produced by variations in the concentration of trace impurities such as iron, manganese, or organic matter, or they may result from variations in the crystal size or orientation of the calcite. In some stalagmites, The banding is sufficiently regular and well-defined that individual annual layers can be identified and counted, providing a chronology that extends back thousands or even tens of thousands of years. The study of these growth layers and the information they contain about past environmental conditions has become one of the most important applications of speleothem science, and it will be discussed in considerably more detail in a later portion of this narration. The mineral composition of the drip water from which speleothems are precipitated is not perfectly constant over time, and variations in water chemistry can produce corresponding variations in the mineralogy and crystal structure of the speleothem. Under most conditions, the calcium carbonate in speleothems is deposited as calcite, which is the thermodynamically stable polymorph of calcium carbonate at the temperatures and pressures that prevail in most caves. However, under certain conditions, calcium carbonate may be deposited as aragonite, which is a metastable polymorph that has the same chemical formula as calcite but a different crystal structure. Aragonite deposition in caves is favored by higher temperatures, higher magnesium to calcium ratios in the drip water, and the presence of certain organic compounds or other impurities that inhibit the nucleation of calcite crystals. In some caves, speleothems contain alternating layers of calcite and aragonite, reflecting changes in the conditions of deposition over time. And these mineralogical transitions can provide additional information about past environmental conditions. The process of speleothem formation, then, is one that unfolds on a timescale that is utterly beyond the scope of ordinary human experience. The drops of water that fall from the ceiling of a cave today are participating in the same process that began millions of years ago and that will continue for millions of years into the future. Each drop that falls is identical in its chemistry and its behavior to the billions of drops that have fallen before it and the billions that will fall after it. And each contributes its own infinitesimally small addition to the growing mass of mineral deposit on the cave floor or ceiling. There is no urgency in this process, no deadline, no schedule, and no possibility of failure. The water will continue to drip, the calcium carbonate will continue to precipitate, and the formations will continue to grow at the same steady, unhurried pace, for as long as the conditions that sustain them persist, which is to say, for a very, very long time indeed. The caves that contain these remarkable formations are found on every continent of the Earth, including Antarctica, and they range in size from tiny crevices barely large enough to admit a human hand to vast underground networks that extend for hundreds of kilometers through the rock. Among the most famous and extensively studied cave systems in the world are the Carlsbad Caverns in southeastern New Mexico, which were designated a national park in the United States in 1930 and which contain some of the most impressive speleothem formations to be found anywhere on Earth. The main chamber of Carlsbad Caverns, known as the Big Room, is one of the largest underground chambers in the world, measuring approximately 1,219 meters in length, 190 meters in width, and 107 meters in height at its tallest point. The floor area of the big room encompasses approximately 33,210 square meters, which is roughly the equivalent of 14 football fields, and the chamber is decorated with an extraordinary profusion of stalactites, stalagmites, columns, draperies, and other speleothem types that have been forming for approximately 4 to 6 million years. The geological history of Carlsbad Caverns is somewhat unusual in that the caves were formed not by the carbonic acid dissolution process that is responsible for the majority of limestone caves worldwide, but rather by a process involving sulfuric acid. The limestone in which the caverns are located, which belongs to the Capitan Reef Formation and is approximately 250 to 280 million years old, dating to the Permian period, was dissolved by sulfuric acid that was generated by the oxidation of hydrogen sulfide gas rising from petroleum deposits in the deeper rock layers below. This sulfuric acid dissolution process, which is known as hypogenic speleogenesis, produced caves with characteristically large, rounded chambers and smooth walls, and it accounts for the exceptionally spacious dimensions of the big room and other chambers in the Carlsbad system. The speleothems that decorate the caves, however, were formed by the more conventional process of calcium carbonate precipitation from carbonic acid-bearing groundwater, and they postdate the initial formation of the cave chambers by a considerable margin. The Mammoth Cave System in central Kentucky is the longest known cave system in the world, with more than 680 kilometers of surveyed passages as of 2024, and new passages continue to be discovered and mapped at a rate of several kilometers per year. The cave is developed in Mississippian age limestone that is approximately 325 to 340 million years old, and the formation of the cave passages began approximately 10 million years ago during the late Miocene epoch. Mammoth Cave was designated a national park in 1941 and a UNESCO World Heritage Site in 1981, and it receives approximately 500,000 visitors per year. The cave is notable not only for its extraordinary length, but also for the diversity of its geological features, which include extensive flowstone deposits, massive columns, delicate gypsum formations, and a variety of unusual speleothems that are found in few other caves. The cave also contains significant archaeological deposits, including evidence of Native American exploration and use of the cave dating back approximately 5,000 years. In Europe, the Postojna cave system in Slovenia is one of the most visited show caves in the world, receiving approximately 700,000 visitors per year and having been open to tourism since 1819, making it one of the oldest tourist caves in the world. The cave system extends for approximately 24 kilometers and is notable for its spectacularly decorated chambers, which contain an abundance of large stalactites, stalagmites, and columns, many of which are brilliantly white due to the exceptional purity of the limestone from which they are formed. The Postojna cave is also famous for its population of olm, a cave-dwelling amphibian with the scientific name Proteus anguinus, which is one of the most remarkable troglodytic organisms known to science and which will be discussed in more detail shortly. The cave was the site of some of the earliest scientific investigations of cave biology, and it remains an important center for speleological research to this day. The Waitomo Caves in the North Island of New Zealand are famous for a rather different reason than most show caves, as their primary attraction is not their speleothem formations, but rather their population of glowworms. The larvae of the fungus gnat Arachnicampa luminosa, which produce bioluminescent light that illuminates the cave ceiling with thousands of tiny blue-green points of light. The effect has been described as resembling a starry night sky, and it attracts approximately 500,000 visitors per year. The caves themselves are formed in Oligocene age limestone that is approximately 30 million years old, and they contain a variety of speleothem formations in addition to the glowworm displays. The Waitomo glowworm cave was first explored by local Maori chief Tain Tinera and English surveyor Fred Mace in 1887, and it was opened to tourists in 1889. The Lechuguilla Cave in New Mexico, located in the same Guadalupe Mountains region as Carlsbad Caverns, is widely regarded by speleologists as one of the most beautiful and scientifically important caves in the world. The cave extends for approximately 241 kilometers and reaches a depth of approximately 489 meters, making it the deepest known limestone cave in the continental United States. Lechuguilla Cave is particularly notable for its extraordinary diversity of rare and unusual speleothem types, including massive gypsum chandeliers, delicate aragonite formations, hydromagnesite balloon-like structures, and subaqueous formations that were deposited in underground pools. The cave is not open to the general public and can be visited only by approved scientific researchers, a policy that has helped to preserve its formations in a nearly pristine condition. In Southeast Asia, the caves of Gunung Mulu National Park in Sarawak, Malaysian Borneo, are among the most impressive in the world. The Sarawak Chamber, located within the Gunung Mulu cave system, is the largest known underground chamber by area, measuring approximately 700 meters in length, 400 meters in width, and at least 70 meters in height, with a floor area of approximately 154,500 square meters. The Deer Cave, also in Gunung Mulu, has one of the largest cave passages in the world, with a cross-section measuring approximately 174 meters in width and 122 meters in height at its largest point. These caves are developed in massive Miocene age limestone and contain a variety of impressive speleothem formations, as well as enormous populations of bats that number in the millions. The study of speleothems as archives of past climate conditions, known as speleothem paleoclimatology, has emerged over the past several decades as one of the most important and productive areas of research in the earth sciences. The fundamental principle underlying this field is that the chemical and isotopic composition of the calcium carbonate deposited in speleothems is influenced by the environmental conditions that prevailed at the time of deposition, and that by analyzing the composition of successive growth layers within a speleothem, it is possible to reconstruct a detailed record of how those environmental conditions changed over time. The most widely used geochemical proxy in speleothem paleoclimatology is the ratio of the two stable isotopes of oxygen, oxygen 18 and oxygen 16, which is conventionally expressed as delta O18, a measure of the deviation of the oxygen isotope ratio from a standard reference value. The oxygen isotope ratio of speleothem calcite is influenced by two main factors: the oxygen isotope ratio of the drip water from which the calcite was precipitated, and the temperature at which precipitation occurred. The oxygen isotope ratio of the drip water, in turn, is primarily determined by the oxygen isotope ratio of the rainfall that feeds the cave system, which is itself influenced by a variety of factors, including the temperature at which the rain formed, the distance of the rainfall source from the ocean, the altitude of the site, and the amount of rainfall. These multiple influences make the interpretation of speleothem oxygen isotope records somewhat complex, but with careful analysis and comparison with other climate proxy records, it is possible to extract valuable information about past temperatures, rainfall amounts, and atmospheric circulation patterns. The dating of speleothems is most commonly accomplished using the uranium-thorium method, also known as UTH dating or uranium series dating. This method relies on the fact that uranium is slightly soluble in water and is therefore incorporated into the crystal structure of speleothem calcite during precipitation, while thorium is essentially insoluble in water and is therefore absent from the calcite at the time of its formation. Over time, the uranium atoms in the calcite undergo radioactive decay, producing thorium-230 as a daughter product. By measuring the ratio of thorium-230 to uranium-234 in a sample of speleothem calcite and applying the known decay constants of these isotopes, it is possible to calculate the time that has elapsed since the calcite was deposited. The uranium-thorium method can provide precise and accurate ages for speleothems that are up to approximately 600,000 years old, with typical analytical uncertainties of less than 1% for young samples and a few percent for older samples. For speleothems older than 600,000 years, the uranium lead dating method can be employed, which extends the datable range to several million years. The combination of high-precision uranium-thorium dating with detailed measurements of oxygen isotope ratios and other geochemical proxies along the growth axis of a stalagmite can produce climate records of remarkable detail and temporal resolution. Some of the most important speleothem climate records have been obtained from caves in China, where stalagmites from caves such as Donga Cave, Hulu Cave, and Sambao Cave have provided continuous records of the East Asian monsoon system that extend back more than 640,000 years. These records have revealed a strong correlation between monsoon intensity and variations in the Earth's orbital parameters, confirming the Milankovitch theory that cyclic changes in the Earth's orbit around the Sun are a primary driver of long-term climate variability. The temporal resolution of these records is in some cases better than that of ice core records, which have traditionally been the gold standard for paleoclimate reconstruction. And speleothem records have the additional advantage of being available from tropical and subtropical regions where ice cores cannot be obtained. Speleothem climate records have also been obtained from caves in many other parts of the world, including Europe, the Americas, the Middle East, Africa, and Australasia. And these records have contributed significantly to our understanding of past climate variability on both regional and global scales. In particular, speleothem records have provided important information about the timing and magnitude of abrupt climate changes, such as the Dansgaard-Oeschger events and Heinrich events that punctuated the last glacial period, and about the response of tropical rainfall patterns to changes in northern hemisphere ice sheet extent. Beyond their role as climate archives, caves also support unique and fascinating ecosystems that have been the subject of scientific study for more than 2 centuries. The ecological communities that inhabit caves are among the most specialized in the natural world, as the organisms that live in the deep interior of caves must cope with a set of environmental challenges that are radically different from those faced by surface-dwelling organisms. The most obvious of these challenges is the complete and permanent absence of light, which means that photosynthesis is impossible and that the base of the food web in cave ecosystems must be supplied by other means. In most caves, the primary source of food energy is organic matter that is transported into the cave from the surface, either by water flowing through the cave, by animals that enter and leave the cave, or by the roots of plants that penetrate into the cave from above. In a few exceptional cases, cave ecosystems are supported by chemosynthetic bacteria that derive energy from chemical reactions involving hydrogen sulfide or other inorganic compounds. But these chemosynthetic ecosystems are relatively rare and are found only in caves with specific geological and hydrological characteristics. The organisms that are permanently confined to cave environments, known as troglobites, have evolved a remarkable suite of adaptations to their lightless, food-limited world. Many troglobites have completely lost their eyes, or retain only vestigial, non-functional eye structures, because the metabolic cost of developing and maintaining functional eyes cannot be justified in an environment where there is no light to see. Similarly, many troglobites have lost their body pigmentation, becoming pale white or translucent, because the pigments that protect surface-dwelling organisms from the damaging effects of ultraviolet radiation serve no purpose in the perpetual darkness of a cave. In compensation for the loss of vision, many troglobites have evolved greatly enhanced non-visual sensory abilities, such as elongated antennae, sensory hairs, or lateral line systems that allow them to detect vibrations, chemical gradients, and air currents in their dark environment. The olm, Proteus anguinus, which inhabits the caves of the Dinaric karst region of southeastern Europe, including the Postojna cave mentioned earlier, is perhaps the most famous troglobitic organism in the world. The olm is a neotenic amphibian, meaning that it retains its larval features throughout its adult life, including external gills that it uses for respiration in the cave waters where it lives. Adult olms are typically 20 to 30 centimeters in length, although individuals as long as 40 centimeters have been recorded. They're entirely devoid of body pigmentation, giving them a translucent, pinkish-white appearance, and they have greatly reduced eyes that are covered by a layer of skin and are essentially non-functional. Despite their apparent simplicity, olms are remarkably long-lived, with estimated lifespans of 58 to over 100 years, which is extraordinary for an amphibian of their size. They are also capable of surviving for extended periods without food, with some individuals reportedly going as long as 10 years without eating, an adaptation that is presumably related to the scarcity of food resources in their cave environment. Other notable troglobites include the Texas blind salamander, Uracea rathbunni, which is found only in the water-filled caves of the Edwards Aquifer in central Texas, and which has been listed as an endangered species since 1967. The cave crayfish of the genus Cambrus, several species of which are found in caves throughout the southeastern United States, and numerous species of cave spiders, cave beetles, cave millipedes, and cave-adapted fish that are found in caves on every inhabited continent. Many troglobitic species have extremely limited geographic ranges, being known only from a single cave or a small group of nearby caves, and they are consequently among the most vulnerable organisms on Earth to extinction from habitat destruction or environmental change. The conservation of cave environments and their formations has become an increasingly important concern as human activities have expanded into areas that were once remote and inaccessible. Caves and their speleothems are vulnerable to damage from a variety of human activities, including tourism, mining, quarrying, groundwater extraction, pollution, and vandalism. The formations that have taken hundreds of thousands of years to grow can be destroyed in moments by a careless touch, an act of vandalism, or a change in the hydrological conditions that sustain them. Human body heat, exhaled carbon dioxide, and artificial lighting can alter the temperature, humidity, and carbon dioxide concentration in a cave, potentially disrupting the delicate chemical equilibria that controls speleothem growth. Studies at show caves around the world have documented measurable changes in cave microclimate caused by the presence of large numbers of visitors, including temperature increases of several degrees, reductions in humidity, and increases in carbon dioxide concentration to levels several times higher than the natural background. The effects of increased carbon dioxide on speleothem formations can be particularly insidious, as elevated carbon dioxide levels in the cave atmosphere shift the chemical equilibrium of the calcium carbonate system in the direction of dissolution rather than precipitation. In other words, the very process that creates speleothems can be reversed by human activity, causing formations that have been growing for millennia to begin dissolving instead. This phenomenon, known as dissolution corrosion, has been documented at several heavily visited show caves, where visible etching and deterioration of speleothem surfaces has been observed in areas near tourist walkways and gathering points. The contamination of cave drip water by pollutants from the surface, including agricultural chemicals, sewage, petroleum products, and heavy metals, can also affect the chemistry and growth of speleothems and, in severe cases, can render cave ecosystems uninhabitable for the specialized organisms that depend on them. Groundwater extraction from aquifers that feed cave systems can lower the water table and reduce or eliminate the supply of drip water to the cave, causing speleothem growth to cease entirely. Quarrying and mining operations that remove limestone from the vicinity of caves can alter the hydrology of the area and may physically destroy caves and their contents. In recognition of these threats, many countries have enacted legislation to protect caves and their formations. In the United States, the Federal Cave Resources Protection Act of 1988 provides legal protection for caves on federal lands and establishes penalties for the destruction, defacement, or removal of cave formations. Similar legislation exists in many other countries, and international organizations such as the International Union of Speleology and the National Speleological Society have developed guidelines and best practices for the management and conservation of cave resources. Many show caves have implemented visitor management strategies designed to minimize the impact of tourism on the cave environment, including limiting the number of visitors per day, controlling the duration of visits, using low-heat LED lighting instead of incandescent bulbs, and monitoring cave microclimate parameters on an ongoing basis. The management of lighting in show caves has proven to be a particularly challenging aspect of cave conservation. Early show caves were illuminated with candles, torches, or oil lamps, all of which deposited soot and smoke residues on cave walls and speleothem surfaces, causing permanent discoloration that is still visible in many of the world's oldest tourist caves. The introduction of electric lighting in the late 19th and early 20th centuries eliminated the problem of soot deposition, but introduced a new and, in some ways, more insidious threat: the growth of photosynthetic organisms, including algae, mosses, and ferns on cave surfaces that were never intended to support such life. These organisms, collectively known as lampenflora, thrive in the artificially illuminated zones of show caves, forming green patches and biofilms that can corrode and discolor speleothem surfaces, and that detract from the natural appearance of the cave. The management of lampenflora typically involves regular cleaning of affected surfaces, the use of ultraviolet filtering glass over light fixtures, and the adoption of LED lighting systems that emit minimal wavelengths in the photosynthetically active range. The monitoring of cave environments has become increasingly sophisticated in recent decades, with many show caves now equipped with networks of sensors that continuously record temperature, humidity, carbon dioxide concentration, airflow velocity, and drip water chemistry at multiple locations throughout the cave. The data collected by these monitoring systems provide a detailed picture of how the cave environment responds to natural seasonal cycles and to the presence of human visitors, and they allow cave managers to detect and respond to potentially harmful changes in cave conditions before irreversible damage occurs. In some caves, The monitoring data have been used to develop mathematical models of cave microclimate that can predict the effects of different visitor management strategies on the cave environment, allowing managers to optimize the balance between public access and environmental protection. Despite these conservation efforts, the global loss of cave resources to human activity continues at an alarming rate, particularly in developing countries where caves may be viewed primarily as sources of guano for fertilizer, limestone for cement production, or minerals for commercial exploitation. The destruction of caves and their ecosystems represents an irreversible loss, as the formations and organisms that are destroyed can never be recreated within any time frame that is meaningful from a human perspective. A stalactite that took 100,000 years to grow and that is broken off by a thoughtless tourist or a careless miner is, for all practical purposes, gone forever, and the climate record that it contained is lost beyond any possibility of recovery. The mineralogy of speleothems is, for the most part, dominated by calcite, the most thermodynamically stable polymorph of calcium carbonate under the conditions of temperature and pressure that prevail in the vast majority of caves. However, more than 250 different mineral species have been identified in cave environments, and the diversity of speleothem mineralogy is considerably greater than might be suggested by the predominance of calcite in most cave decorations. Aragonite, the second most common calcium carbonate polymorph found in caves, has already been mentioned in passing, and it deserves somewhat more detailed consideration. Aragonite crystallizes in the orthorhombic crystal system, as opposed to the trigonal system of calcite, and it forms needle-like or acicular crystals that are quite distinct in appearance from the blocky or rhombohedral crystals of calcite. In caves, aragonite typically occurs as clusters of radiating needle crystals, sometimes called frostwork or anthodites, that project outward from cave walls and ceilings in delicate, bush-like or flower-like sprays. These aragonite formations can be extremely beautiful and fragile, and they are among the most prized of all cave decorations by speleologists and cave photographers. The conditions that favor aragonite precipitation over calcite precipitation in caves have been the subject of considerable research, and several factors have been identified as being important. High concentrations of magnesium in the drip water appear to be one of the most significant factors, as magnesium ions are known to inhibit the nucleation and growth of calcite crystals, while having relatively little effect on aragonite crystallization. When the magnesium to calcium ratio in the drip water exceeds a certain threshold, which is typically in the range of 1 to 1 to 2 to 1, the nucleation of calcite is effectively suppressed, and calcium carbonate precipitates as aragonite instead. Higher temperatures also favor aragonite precipitation, as the solubility of aragonite relative to calcite decreases with increasing temperature, and aragonite becomes the kinetically preferred precipitate at temperatures above approximately 30 to 40 degrees Celsius in the absence of other modifying factors. The presence of certain organic compounds, sulfate ions, and strontium ions in the drip water can also promote aragonite crystallization. Gypsum, a hydrated calcium sulfate mineral with the chemical formula CaSO4 multiplied by 2H2O, is another mineral that is commonly found in caves, particularly in caves that have formed by sulfuric acid dissolution or in caves in arid regions where evaporation is significant. Gypsum speleothems can take a variety of forms, including massive crystalline deposits, delicate needle-like crystals, and thin, curving blades or flowers that project from cave walls. The Cave of the Crystals, or Cueva de los Cristales, in the Nica mine in Chihuahua, Mexico, contains the largest known gypsum crystals in the world, with individual selenite crystals measuring up to 12 meters in length, 4 meters in diameter, and weighing approximately 55 metric tons. These extraordinary crystals formed over a period of approximately 500,000 years in a water-filled chamber at a depth of approximately 300 meters below the surface, at a temperature of approximately 58 degrees Celsius. Under conditions of extreme geological stability that allowed the crystals to grow to their present remarkable dimensions. The cave was discovered in 2000 by miners drilling a new tunnel, and it has been the subject of extensive scientific investigation. Although access to the cave is extremely difficult due to the near-lethal combination of high temperature and 100% humidity that prevails in the crystal chamber. Among the most peculiar and scientifically intriguing of all speleothem types are helictites, which are formations that appear to defy gravity by growing in directions other than vertically downward. While stalactites always grow downward under the influence of gravity, and stalagmites always grow upward, helictites may grow sideways, upward, downward, or in spiraling, twisting, seemingly random directions that give them a distinctly eccentric appearance. The mechanisms that control helictite growth are not entirely understood, but the most widely accepted hypothesis is that capillary forces, rather than gravity, are the primary driving force. In this model, water is drawn through a very narrow central canal in the helictite by capillary action, and the direction of growth is determined by the interplay of capillary forces, crystal growth kinetics, and small-scale variations in the porosity and permeability of the calcite at the growing tip. Because capillary forces can act in any direction, helictites are not constrained to grow vertically, and the complex, curving forms that result are a consequence of the constantly shifting balance of forces at the growing tip. Helictites are found in caves worldwide, but they are particularly abundant in certain caves where conditions favor their formation, such as Lechuguilla Cave in New Mexico, where entire chambers are decorated with forests of helictites in a bewildering variety of shapes and sizes. Some helictites are simple curved or bent rods, while others form complex spirals, corkscrews, or branching structures that resemble underwater coral. The central canal through which water flows in a helictite is typically very narrow, on the order of 0.1 to 0.5 millimeters in diameter, and the external diameter of a helictite is usually only a few millimeters, although some larger examples may reach a centimeter or more in thickness. The growth rate of helictites has been estimated at approximately 0.01 to 0.1 millimeters per year, which is even slower than the growth rate of most stalactites and stalagmites. Cave pearls are another unusual type of speleothem that forms under specific hydrological conditions. A cave pearl is a small, roughly spherical concretion of calcium carbonate that forms in a shallow pool of water on the floor of a cave, typically in a basin or depression where drip water collects. The pearl forms around a nucleus, which may be a grain of sand, a small fragment of rock, or a tiny piece of bone or other foreign material. And it grows by the successive deposition of concentric layers of calcium carbonate as the drip water in the pool slowly precipitates its dissolved mineral content. The spherical shape of cave pearls is maintained by the gentle agitation of the water in the pool, which is caused by the impact of dripping water from above. This agitation periodically rotates the pearl, ensuring that mineral deposition occurs relatively evenly on all sides and preventing the pearl from becoming cemented to the floor of the pool. Cave pearls range in size from less than a millimeter to several centimeters in diameter, and they are sometimes found in clusters or nests containing dozens or even hundreds of individual pearls. Moo milk is yet another unusual cave deposit that defies easy classification. Moon milk is a soft, putty-like or cottage cheese-like substance that is found coating the walls, ceilings, and floors of some caves, and it is composed of a mixture of fine-grained carbonate or sulfate minerals, water, and in many cases, microorganisms. The mineralogy of moon milk is variable, but the most common mineral constituents are hydromagnesite, huntite, calcite, and nescahenite. The texture of moon milk ranges from a wet, viscous paste when freshly formed to a dry, chalky powder when desiccated, and it can accumulate in deposits that are several centimeters to several meters thick. The role of microorganisms in moon milk formation has been the subject of considerable debate, with some researchers arguing that moo milk is primarily a biogenic deposit produced by the metabolic activity of bacteria and fungi, while others contend that it is primarily an inorganic precipitate that merely provides a substrate for microbial colonization. The truth likely lies somewhere between these two positions, as there is evidence that both biological and inorganic processes contribute to moon milk formation, with the relative importance of each varying depending on the specific conditions at each site. The history of human exploration of caves extends back to the very earliest periods of human prehistory, as evidenced by the cave paintings and other archaeological remains that have been found in caves on every inhabited continent. The paintings in the Lascaux cave in France, which date to approximately 17,000 years ago, and those in the Altamira cave in Spain, which date to approximately 14,000 to 36,000 years ago, are among the most famous examples of Paleolithic cave art, but hundreds of other decorated caves are known from Europe, Asia, Africa, Australia, and the Americas. These early humans clearly ventured deep into caves, far from the entrance and the light of day, and their motivations for doing so, whether religious, artistic, or utilitarian, remain the subject of scholarly debate. The cave formations that these early explorers encountered in the depths of the earth must have been objects of wonder and perhaps spiritual significance. And it is tempting to speculate about the impression that a chamber full of stalactites and stalagmites might have made on a person who had no scientific framework for understanding how they formed. The systematic scientific exploration of caves began in earnest during the 17th and 18th centuries, when natural philosophers in Europe began to investigate the geological processes responsible for cave formation and speleothem growth. One of the earliest scientific descriptions of cave formations was provided by the English physician and naturalist Thomas Brown in his 1658 work The Garden of Cyrus. Although his understanding of the processes involved was necessarily limited by the state of chemical and geological knowledge at the time, the French naturalist Georges-Louis Leclerc, Comte de Buffon, discussed cave formations in his monumental Histoire naturelle, published in multiple volumes between 1749 and 1804. And the German mineralogist Abraham Gottlob Werner provided one of the first systematic classifications of cave minerals in the late 18th century. The development of modern speleology as a scientific discipline is generally attributed to the French cave explorer Edouard Alfred Martel, who is often referred to as the father of modern speleology. Martel conducted extensive explorations of caves in France and other European countries during the late 19th and early 20th centuries, and he published numerous scientific papers and books describing his findings. He was the first to systematically document the geological, hydrological, and biological features of the caves he explored, and he developed many of the techniques and methods that are still used in cave exploration today. Martel founded the Société de Spéléologie in Paris in 1895, which was the first speleological society in the world, and his work laid the foundation for the rapid development of speleology as a recognized scientific discipline during the 20th century. Modern cave surveying and mapping techniques have advanced considerably since Martel's time, and contemporary speleologists have access to a range of sophisticated tools and technologies that allow them to produce highly accurate three-dimensional maps of cave systems. Traditional cave surveying involves measuring the direction, inclination, and length of each segment of a cave passage using a compass, clinometer, and measuring tape, and then plotting these measurements on a map. This process is laborious and time-consuming, but it remains the standard method for cave surveying in most parts of the world. And the accumulated survey data for many of the world's major cave systems represent decades of painstaking effort by thousands of volunteer cavers. More recently, terrestrial laser scanning, also known as LiDAR, has been applied to cave surveying, and this technology can produce three-dimensional point cloud models of cave passages with millimeter-level accuracy. Photogrammetric techniques, in which three-dimensional models are reconstructed from overlapping photographs, have also been applied to cave documentation with considerable success. The cultural significance of caves extends far beyond their role as sites for prehistoric art and habitation. In many cultures around the world, Caves have been regarded as sacred or spiritual places, associated with gods, spirits, ancestors, or the underworld. The ancient Greeks believed that caves were the entrances to Hades, the underworld of the dead, and several Greek myths, including the story of Orpheus and Eurydice, involved journeys into cave-like underworlds. In Mayan culture, caves were considered to be portals to Xibalba, the realm of the dead, and extensive archaeological evidence of ritual activity has been found in caves throughout the Mayan region of Central America. In Hinduism, several important cave temples, such as the Ajanta and Ellora caves in India, have been carved from living rock and decorated with elaborate sculptures and paintings. And these cave temples continue to serve as sites of worship and pilgrimage to this day. In European folklore, caves were often associated with dragons, giants, dwarves, and other mythical creatures, and the strange mineral formations found in caves undoubtedly contributed to these legends. Stalactites and stalagmites, with their organic, almost anatomical shapes, could easily be interpreted as the petrified remains of supernatural beings and the echoing darkness of cave interiors, the dripping of water, and the occasional gust of wind from hidden passages must have contributed to the sense of mystery and unease that caves have evoked in human minds for millennia. The use of caves for practical purposes, beyond habitation and spiritual practices, has a long history as well. Caves have been used as storehouses and refrigerators, taking advantage of their constant cool temperatures to preserve food and other perishable goods. In some regions, caves have been used as sources of mineral deposits, including saltpeter, which was mined from cave sediments for use in the manufacture of gunpowder, and bat guano, which has been collected from caves as a rich source of nitrogen for fertilizer. During times of war, caves have served as natural shelters and fortifications, providing protection from enemy attack, and many caves around the world bear evidence of military use spanning centuries or even millennia. In more recent times, caves have become important sites for scientific research in a variety of disciplines beyond geology and biology. The extreme environmental conditions found in some caves, including total darkness, constant temperature, minimal vibration, and isolation from electromagnetic interference, make them ideal locations for sensitive scientific instruments and experiments. Several neutrino detectors and other particle physics experiments have been located in underground caverns to shield them from cosmic radiation, and caves have been used as sites for experiments in human physiology, particularly studies of the effects of isolation and the absence of natural light cues on the human circadian rhythm. The use of caves as wine cellars and cheese aging facilities deserves particular mention, as the constant temperature and high humidity of caves provide naturally optimal conditions for the maturation of wine and the aging of certain types of cheese. The famous Roquefort cheese of southern France has been aged in the natural limestone caves of Roquefort-sur-Solzhenn for centuries, where the unique microclimate of the caves, including the specific species of Penicillium roqueforti mold that thrives in the cave environment, imparts the cheese with its distinctive flavor and texture. Similarly, numerous wineries in regions such as Champagne, Burgundy, and the Loire Valley in France, and in the Tokaj region of Hungary, have utilized natural caves or man-made underground cellars carved from limestone for the aging of their wines, taking advantage of the constant temperatures, typically in the range of 10 to 14 degrees Celsius, and the high humidity that prevent the corks from drying out and the wine from oxidizing prematurely. The scientific study of cave atmospheres has revealed that the air inside caves can differ significantly in composition from the atmosphere outside, and these differences have important implications both for speleothem growth and for the safety of cave explorers. In addition to the elevated carbon dioxide concentrations that have already been discussed, cave atmospheres may contain reduced levels of oxygen in poorly ventilated areas where biological or chemical consumption of oxygen exceeds the rate of replenishment from outside. In rare cases, caves may contain dangerous concentrations of radon gas, a naturally occurring radioactive gas that is produced by the decay of uranium and radium in the surrounding rock. Radon concentrations in some caves have been measured at levels of several thousand becquerels per cubic meter, which is many times higher than the levels considered acceptable for continuous human exposure. Cave guides and researchers who spend extended periods in high radon caves may be at increased risk of lung cancer, and radon monitoring has become a standard component of occupational health and safety programs for cave workers in many countries. The contemplation of cave formations and of the geological processes that created them has a quality that is perhaps uniquely suited to the present moment. As the listener lies in the quiet darkness and allows the mind to wander freely through the underground spaces that have been described in the preceding narration, there is something deeply calming about the thought of a process that unfolds with such infinite patience, a process that is measured not in the minutes and hours and days that govern ordinary human life, but in the millennia and epochs that govern the life of the earth itself. The stalactite that has been growing for 100,000 years does not know or care whether anyone is watching it, whether anyone is measuring it, whether anyone finds it beautiful or interesting or boring. It simply grows, drop by drop, layer by layer, in the same darkness and silence that have surrounded it since long before the first human being ever set foot in a cave. The water continues to seep through the rock above, carrying its dissolved burden of calcium and bicarbonate, exactly as it has been doing for millions of years and exactly as it will continue to do for millions of years to come. Each drop that forms on the ceiling of the cave, hangs for a moment, and then falls to the floor below is participating in a cycle that is as old as the limestone itself. A cycle that began when the calcium carbonate was first deposited on the floor of an ancient sea by the accumulated shells of countless tiny marine organisms, was buried and compressed into rock by the weight of overlying sediments, was uplifted and exposed by the slow movements of tectonic plates, was dissolved by the gentle action of carbonic acid in rainwater, and is now being redeposited, molecule by molecule, in the dark interior of a cave that no human eye may ever see. This cycle of dissolution and precipitation, of erosion and deposition, of destruction and creation, is one of the fundamental rhythms of the earth. A rhythm that has been repeating itself since the formation of the first limestone rocks more than 2 billion years ago, and that will continue to repeat itself for as long as water flows over and through the rocks of the Earth's crust. It is a rhythm that is entirely indifferent to the affairs of human beings, a rhythm that proceeded without interruption through the rise and fall of every civilization that has ever existed, and that will proceed without interruption through whatever may come in the future. The stalactites and stalagmites that decorate the caves of the earth are monuments to this rhythm, physical manifestations of a process that is so slow and so steady and so utterly relentless that it seems, in some fundamental way, to belong to a different order of reality than the brief, hurried, anxious existence of human life. And so the water continues to drip, as it has always dripped, and the formations continue to grow, as they have always grown, in the darkness and silence and stillness of the deep earth, untroubled by the passage of time, unaffected by the events of the surface world above, proceeding at the same unhurried pace toward no particular destination and no particular conclusion, simply continuing as they have always continued, for no reason other than that the conditions for their continuation still exist and will continue to exist for a very long time to come.